Is everyone in listen mode then?
Yes.
Okay. Good morning to all those that are in attendance. This is our monthly webinar. We're going to spend an hour together here at Vibrant Technology in our new offices in Centennial, Colorado, which is just south of Denver. We've been here now for a little over a month. My son Mark is going to be the moderator, and I am Mark Richardson. I'm going to be the okay, am I on the air now, Mark?
Yeah, you sure?
Okay, I just had a message pop up that said I
Oh,
was unmuted.
sorry. I was trying to mute myself. Go ahead.
Welcome to everyone. This is Mark Richardson speaking from Vibrant Technology in Centennial, Colorado, a little bit south of Denver. And this is our new headquarters for Vibrant Technology. We've been here a little over a month now, and we're going to spend the next hour together, and I'm going to show you an example of using SDM for substructuring. So I'm going to open up a project here that's called SDM Substructuring. It's a MEscope project I have on my desktop. Well, let me do it this way. I'll start MEscope first, and then we'll just open a file from the desktop. Now, MEscope is coming up in what we call our demo license version. This is not the one that those of you that are not resellers would ever see. This is a little different than the one that you're used to seeing in the about box. This just shows all of the options of MEscope that have been enabled by my license. You can see that it's a VT STN, a 950, which is all of my options are turned on here, all the VES options. Now there's some newer options down here below that are not enabled, but I can turn them on from this demo set of software or with a demo license. But I'm not going to be using any of these. I'm simply going to be using the 8000, the FEA model updating, and the 5000 structural dynamics modification options to show you some of those capabilities in MEscope today. So these are more advanced options, and they're part of the more advanced MEscope packages. If I go back and select, just ODS or modal, let me just select the modal package. You can see that it turns off the 5000 and the 8000 and some of the other options. So this particular webinar this month is going to be a little more advanced, and I'm just going to go back here and choose. You can see all these different packages here. If I go down and choose the STN, it turns on for me or enables a lot of the advanced options, all the advanced modal analysis, the structural dynamics, the acoustics, FEA model updating. Now we've recently changed the title on that. We used to call that experimental FEA, and the implication was that we could use our experimental model and do some FEA work. The real feature in there is using the SDM approach to do model updating. Now we're not going to do that today, but we are going to use the FEA solver to solve for some FEA modes, and then we're going to use structural dynamics modification to attach several substructures together with stiffeners and have SDM compute the new modes of the assembled structure. So that's the power of SDM, is that it only needs mode shapes, and so we can get them from FEA or we can get them from experiment, and we can can do a lot of different things with it. Today we're going to do what's called substructuring. So I'll show you how we can put together the mode shapes from several pieces of a structure, and then use SDM to come up with a set of modes for all the pieces attached together with stiffeners. So that's what we're going to do today. We're going to use some macros and some hotkeys to automate the process. This is a standard part of MEscope now, where you can create macros, and then you can also create hotkeys that execute those macros. So once you have a process set up in MEscope, then you can save hotkeys and macros with your project, and you can come back and repeat the process, many steps, and it's good for demonstrations. It's good for recalling things that you might have done months or years ago and you can't remember how you got the results, but the macro and the hotkeys, all you have to do is hit a hotkey and it will reproduce all your results. So we're going to use that today, and I'll show you some of the programs that we've set up to do that. Okay, I'm going to go ahead and click on OK. So it's going to open up MEscope, and you can see I've got a number of projects that I've been working on here. So we're going to come back and look at these, the VTech SDM substructuring, and then we're going to look at using the mode shapes to expand some ODS data. And we'll look at both of these cases. And you can see there's another one here, a SDM project involving the Jim beam. That's right out of the manual. That's one of the tutorials in the manual, and you can follow those steps. And this one is a project with hotkeys and macros to carry out those steps. I'm going to go ahead and open up this SDM right here. Now, we've got a server here at Vibrant, so we save a lot of these VTPRJs, these projects, in a special library that we can distribute to you, so that if you're attending here today, we can actually send you these VTPRJs, and if you request them, and then you can run them on your system. Now, as I said earlier, you're going to need these advanced options in your software in order to use some of these tools. So this one here is stored on my desktop. I keep putting the mouse over it to see where it is, because there's also a version stored out in the SDM library. So I want to make sure that I get the one off of my desktop that I'm working with. Let me just click on that and open it up. So here it is. Let me arrange some things here and show you what we're looking at. I'll put this down, and let me just make this large. So we'll look at the model here first. Now, this is a model that we use in when we go to conferences, and we actually have the machine here at Vibrant, and we take live data on it, and we use this FEA model to animate this particular machine here. It's a rotating machine. You can see that it's not a photo model, but it's a rather detailed solid model. It was built in MEscope using the tools in MEscope. The other thing that it has in it are some of these substructures. You can see there's a lot of parts to this model, all broken up into various pieces. And if I start the animation where there's no animation source, then it will simply rotate the parts on the model that have been set up to rotate. So there's a little bit of work here involved in doing this. Now you can see those rotor parts over here. If I look in this spreadsheet, you can see that there's a number of parts: a shaft pulley, inboard rotor, outboard rotor, and motor pulley. All these are set up to rotate. This button is pressed here, and that's why they're rotating when the animation starts. and they're rotating at different speeds. That's also something that's set in here. Now the animation, if I animate ODS data, which is typically order related ODS data, the parts will rotate at the same frequency. They'll complete one cycle of rotation as the animation if I'm looking at the first order ODS data. So if I go to second order, then the second order data will animate twice as fast as the rotation and so forth. So we've tied this in. This is for rotating equipment so that we can look at order-based deflections. And but what we're going to do here today is actually work with the other part of this model, which is hidden underneath, and that is an FEA model of the bearing blocks and the base plate. And what we're going to do here is we're going to build this up in 3 pieces. We're going to we're going to put some solid elements, some brick elements, and some prism elements onto each of the bearing blocks. And that's already been done. And some brick elements on the base plate. Solve for the FEA modes of each of these parts. And then use SDM with some stiff springs to attach each of the bearing blocks to the base plate. So that's what we call substructuring. And rather than go through the myriad steps needed to do that, I've created some hotkeys here in this project. And I've got the mouse up here. Now these hotkeys are created with the macro library. That's a standard part of all MEscopes now. So if I go in here and look at these hotkeys, here's the hotkey setup. Here's where they've been defined. And I can, it's just a spreadsheet. I can add more hotkeys if I want. I've given each one of them a name. So the first hotkey is going to solve for the inner bearing block FEA modes. And it's going to call a macro called inner bearing modes. And then it's got some other things here, descriptions and some icons. So those are the same ones that I've chosen that are up here on the toolbar. So if I go up here to the toolbar, I can see inner bearing FEA modes. The second one is outer bearing FEA modes. The third one is base plate FEA modes. The fourth one is substructuring mode shapes. So we'll look at how the mode shapes have to be essentially put together in one shape table to represent the unmodified structure. And then we're going to use SDM to calculate the new modes. So these are the 5 keys. Let me just press 1 now, and this one's going to go execute this program called inner bearing modes, and we'll see what happens. All right, it's come up here and it selected just the FEA model for me, so it went in and made sure that nothing else on the model was visible. All these other substructures were hidden, and it says now we're going to calculate the FEA modes of the inner bearing block. So it's going to go through some more steps. Okay, it's hidden everything. It says some points have no animation equations. Do you want to interpolate? And I'm going to say no. And we'll just go ahead and okay, so we've got the hotkey set up here that's taken up some space. I should have closed that, and the program would have shown me all of this. So here we've got some animation. You can see the elements are on these 3 different pieces, but we've only solved for the modes of one of the bearing blocks. So here I am clicking through. These are rigid body modes of the bearing block. You can see the spring elements there that are attaching it. We'll get to those in a minute. They're not being used yet. Only the bearing block itself is being used, and those elements in the FEA solver to come up with it. So the first 6 modes here are what we call rigid body modes. There's the first flexible mode of the bearing block, and it's at a very high frequency. Let me expand this out a little bit. 4,700 hertz. These are aluminum pieces. They're relatively small. There is the next mode, a bending mode. And as we go up in frequency, you can see the various modes of this bearing block. Now that's just in space. There's no constraints on it. It's not constrained to the base plate yet. Those are just the modes of the bearing block all by itself. Now let's go take a look at I've got some pictures in here that I probably should have showed you first. Okay, well this is the equipment we use to measure ODS data on this machine. It's a variable speed machine, and you can see the accelerometers. There's in this picture there's 6 on the base plate and 1 on each bearing block. So there is what, 8 times 3, there's 24 channels of data being acquired. And down here actually there's 25 because we've got a tachometer, which is measuring the RPM of this machine. So as the machine changes speed, it vibrates differently. It's sitting on some rubber mounts, so you could say that it's experiencing some soft foot, what's called soft foot, because of the soft mounting. A machine mounted in a factory would have, rigid mounting typically. So here's the analyzer that was collecting the data, or it's in one of our portable monitoring boxes. So that's the machine that the live data was taken off of. Now, as I said, part of this model is this FEA model that's going to be used to animate the machine model using interpolation and then using the mode shapes of just the 3 pieces here, the bearing blocks and the base plate. So this one gave me a set of modes for the bearing block, the inner bearing block. Now I'm going to go and press this hotkey here, and it's going to go through a number of steps. Here it's stopped, and this is a user dialog, a macro user dialog that I've added to the macro, and it's going to calculate the FEA modes of the outer bearing block. So we'll go ahead and let that work, and we get the picture here. Let's just move this over so we can look at the data a little better. It set the animation up for me, and that all came out of the macro. And here are the modes of the outer bearing block. They should be identical, really, in terms of their frequencies and their mode shape, because the way we created this model was to simply take one of the bearing blocks and populate it with FEA elements, and then just copy it and paste it into the position of the other bearing block. A little bit of animation here, a little too much motion, so I'm going to turn that down a little bit. But these are the modes. There's 20 modes. We told it to compute the first 20 modes. So this is the FEA solver in MEscope. Not a replacement for Nastran, but very usable for getting some analytical mode shapes to compare with our experimental data. And in this case, we're going to use the analytical mode shapes to expand our experimental data by curve fitting it. Okay, let's go on to the third hotkey here, calculate the FEA modes of the base plate. So there's the base plate, and now you can see those springs that are part of the model. We're not using them yet. STM hasn't been run yet. We're simply solve for the modes of the base plate. You can see again, it's just like the bearing blocks. It's got 6 rigid body modes. Those came right out of the FEA solver. And then the 7th mode is the first bending mode, which is what we'd expect to see from a plate like this. And then there's the first torsion mode. So simple geometry, first bending, first torsion, very good mode shapes. Typically the frequencies might be a little different than what we would see experimentally. That's where we use something like FEA model updating to change some of the properties of the FEA model so that it matches the experimental data. So that's part of this FEA or the VES 8000 option, where we use SDM in a different way to update the FEA model. So you can see these, I'm just clicking through the modes here. These are the modes of the plate. Now we've got all the modes. We've got 20 modes in each case, 20 modes of the plate, 20 modes of each of the bearing blocks. Now I'm going to go to this next hotkey, and it says Substructuring Mode Shapes. So in order to use SDM, I have to have a complete modal model of the structure that I want to now use SDM to compute new modes for. So this says in this dialog, all modes of the unmodified structure have been added to one shape table. So we just do that using cut, copy, and paste commands in MEscope, and now we're displaying the spring elements here too. Let me speed this up just a little bit. You can see things a little better. So here is the model showing the spring elements, the FEA elements, the brick elements, the prism elements of each. But what we're animating here is all of the data together. So now we have a mode shape table with 60 modes in it. Let's make this large so we can take a look at it here. So if I go for the first 20 modes, those are the modes of the base plate. Now let's go back and use the animation. Now I'm going to click on mode number 21. Well, there's a mode that's one of the modes of the inner bearing block. If I go all the way down here and click on number 41, there is a mode of the outer bearing block. You can see that we've got all these different modes in here. A little bit of a display issue, that bearing block points are not moving the way I would expect them to. Let's try that again. I'm going to go back and press this hotkey again and see what happens. Well, we got pretty much the same thing. Let's go down here and look at one of these bearing block modes. All right, well, that picture doesn't look quite the way I wanted it to, but let's just go on and see whether SDM now can see this bearing block here is completely free of the base plate, which it should be. All of its points are not connected to the base plate. And then base plate modes. See, we're not using the springs. Now the springs are going to connect between the top and the bottom. Let's go ahead and calculate new modes. And then we'll come back and look at some of this in detail. Okay, it says SDM will calculate new modes using 36 stiffeners between the bearing blocks and the base plate. Now I'm going to have to go ahead and click here, and then we'll come back and we'll look at it again. Oh boy. That did not work. That did not work. We've got a problem here with this bearing block. It's not. The points on the bearing block are not correct. And you can see the stiffener just is not being applied to that bearing block correctly. Let me close this and reopen it. I think maybe we have an issue here. Here's one of the macros. It's actually the one that's computing the SDM modes. Let me just click on that macro and see if it will give me the result I'm looking for. Yeah, so something happened in one of the earlier steps there. But if I just go to SDM and use the data from each of the substructures that we looked at earlier, here's the result that we should have gotten. That previous, and these are the modes that SDM predicted with the springs attached to the model. And so you can see the first couple are rigid body motion. Now, if we look at it right here, you can see that it's not a symmetrical structure. The bearing blocks are actually mounted on one side of the structure. And as I rotate around, there's another rigid body mode. The blocks are just attached and rigidly moving on as the base plate and the whole assembly rocks in space. Okay, here's mode number 5. Now we're starting to see a little flexure. So we don't have, in this case, necessarily 6 rigid body modes. We got a little bit of flexure here. And you can see the frequency is 116 Hertz. There's another mode that, we expect the first 6 modes to look like rigid body, but we're seeing a little bit of flex of the bottom plate and a little bit of rocking of the bearing blocks on the bottom plate. There's our first real flexible mode, bending of the bottom plate and the bearing blocks just moving with it. Here's our second mode. It's a torsion, but not completely symmetric because those bearing blocks, including their weight, are all being modeled here correctly with the modal model. So another term we use with SDM is that we've started out with a modal model of the 3 substructures, and SDM has modeled the attachment of each of the substructures. Now I could have built this just with an FEA package, but the advantage is that SDM allows me to work with pieces like this. And you notice that the node lines, or the node points, let me put the points on here, and we'll turn off the surfaces. That makes it a little clearer, but the bearing block nodes don't match up with the base plate nodes, what are called nodes in the FEA world. But the springs are modeling the attachment of stiffness between the bearing blocks and the base plate. So we can go on here, and SDM gave us 60 modes, going all the way up to 40,000 hertz. So we got a lot of modes in here, but our fundamental modes are down here in the range of there we can look at them a little clearer. And so we've got some lower frequencies here. I'm up at 600 hertz now. First real flexure starts around 100 hertz, works its way up, and now we've at mode 7 we got first bending, first torsion, a second bending mode. I put the surfaces back on, it looks a little better. So, you know, we want to use this graphical capability in MEscope to look at resonances, and we can see clearly the different modes of this structure. So there's substructuring. Let me just show you how it was done. I'm going to stop the animation. We'll go in here and we'll look at the spring elements. So we've got springs selected up here in our object list, FEA springs. There's 36 of them. Now, they were just manually attached, 12 of them, 6 between each bearing block and the base plate. So if I turn this off, you can see the springs, and they were just randomly attached between points on the bearing block and points on the plate. And then we went over here and changed the direction of stiffness. So the first 12, let's just take the first 12 here. Those are the first 12 springs that were attached. Those were all designed or designated in the X direction. So think of that as a rigid motion in the X direction. Now, when I say rigid, we need to look at the stiffness property of the spring. That is up here in the FEA properties list. And here's the spring. And let me hold down the control and make that a little larger. So here is an FEA spring property of 1,000,000 pounds of force per inch. Now, again, English units, that's a lot of stiffness. I'd have to push down or pull up with 1,000,000 pounds to move it 1 inch. That's what that's saying. So we simply use the copy command here, edit, copy objects to file, and if we do that, I've got the 12 springs selected, and I'll simply add them to the same structure model here, and I'll get a copy of those 12 springs. I'll go ahead and do it here, and you can see that now we've got 48 down here. So I've actually added 12 more springs with the X dimension. So I don't really want those. I'll go back and do an undo here, and we'll remove those springs from the model. Now this is got a lot of stuff in it, so it's taken a minute to undo that edit out of the computer memory. So now we have the 36 springs back, but if I look at the next 36 from 13 to 24, now I need to do that again. I'm going to hold down the shift key and click on 24. So the springs are in the same location. However, they're applying stiffness in the Y direction between all those pairs of points, between all the 6 points on the base over here and the bearing block, and the 6 points on the base here and the bearing block. So that's what we're doing here. And then finally, the last 12 points, let me just highlight those, B26 down to 36, or 25 to 36, sorry. There they're lighting up again, but those are applying stiffness all in the Z direction. So that is what MEscope is, SDM and MEscope is using. I can go back up here and push this button again, and I'm taking the unmodified data. And so here is my unmodified data. Let me see if I can, that should be up here displayed for me. Well, I guess I got to go ahead and calculate. And we're going to end up animating the modified data. I can go back. Let's just go back and try calculating the unmodified, because something occurred in the previous project here and things just didn't work very well. Okay, so here we are with the unmodified mode shapes, and I've got the first 20 are the base plate, the next 20 are the one bearing block, and now everything seems to be working. There's the second bearing block, and you can, it's moving independently of the base plate. Now if I just go here and press the SDM button, okay, so it's still animating the unmodified mode shape, and now I'm going to tell it to go ahead and calculate the SDM modes, and there now I'm looking at the modified mode shapes for the structure. Okay. That is substructuring. Let's go on now. I'm going to open a second project where we use this particular FEA model now of the base plate and the two bearing blocks, and we're going to use it to animate the machine model, the VTech machine model, but we're going to expand the experimental data using this FEA model and then use interpolation to animate the machine model. So let me close this project, save it, no, and here's the other VTech expand 3-speed. So what we mean there is we're going to use this, model now. Okay, it wants to start a macro, but I'm going to say no. Let me arrange the windows, and here is the same model, and there's the FEA model underneath of it. So we built the FEA model off of the machine model itself, at least 3 parts of it. And what we're going to say here is that that is the part of the machine that could flex at certain speeds. And normally we would, and then we're taking data where each of these blue cubes are. So, and we can get live data off of this machine as it runs and track the ODS, what we call the order-based ODS, first order, or any of the higher orders. Now we've already done that. This data is in a shape table. And what I have up here are hotkeys that are going to, well, let me just go ahead and press one and we'll see what it looks like. So now what we have on the left is the animating model where we took the experimental data at the 8 points, 6 on the base plate and 1 on each of the bearing blocks, and we curve fit a modal model to the experimental ODS data, the live ODS data, and now on the left we're animating with interpolation of all the parts. Here, if I go back and show you that this is an ODS, and what this is saying is that the ODS is a linear combination of mode shapes. So we're not using the frequencies, we're simply using the mode shapes. So there is an ODS that we got by curve fitting the actual experimental data. Now on the right is typical animation in MEscope, where we're using geometric interpolation to interpolate between the 8 test points. And it does a pretty good job. Let me put this back, and we can certainly see how the machine deflects at this particular speed. Now this speed is 985 RPM. That's where the data was taken. What we're looking at up here are the MAC values. Let me put these up. The MAC value and the SDI value of these two shapes. On the left is the expanded shape. On the right is the experimental data, the ODS that was taken off of the running speed of the machine, simply saving the peak values from the spectra, from the 24 spectra. On the left is a curve fit. What it's saying is that the curve fit is 87% alike. Both SDI and MAC are giving me the same value. That what it's saying is that the curve fit is matching up with the experimental data at the points where we actually have data, and it's showing me an animation there. Now let's go to the next speed, where we speed the machine up a little bit. Okay, now see how this dropped off? I got a little bug in my macro here. I want to go use all 10 modes of the machine. So now we're seeing at 1400 Hertz. You can see down here that we've got two shape tables. The one below is the 1400 Hertz ODS data. This is my experimental data with the 24 degrees of freedom in it, each of my test points, ODS data, and it's actually in velocity units, so it's been integrated from the accelerometer results. That is the data on the right. The data on the left is the curve fit of 10 of the modes of the base plate and bearing blocks to the ODS data. A much cleaner animation, and it's 91% the same as the original data. So that's a pretty good curve fit. That's showing us that the 10 modes there are matching up well. Let's go to the third case, and I may have to, you can see this dropped off. I need to go back and select the 10 modes and do the curve fit over again. And this one is even a closer match. At 2280 RPM, the curve fit of the modal model to the operating data is 94%. Now, SDI actually matches up the numerical values. The MAC just says that the shapes are the same. The shapes lie along the same straight line. Doesn't matter what their magnitudes are. SDI is actually matching up the true magnitude of the expanded ODS with the experimental. So now these other three keys here allow me to simply select two of the modes of the modal model, which would be two of the rigid body modes, six of the rigid body modes, and we saw the modal model actually had some flex in it for modes 5 and 6, or all 10 of the first modes, which would be essentially 6 rigid body modes and 4 flexible modes, curve fitting all those mode shapes to the experimental data. This is what we call shape expansion in MEscope, and that's one of the commands in a shape table. If I just go here to a shape table and look at under my tools menu, here's the command that's doing it right here. It's called shape expansion. So that's taking the mode shapes and expanding the ODS data. We can use it to expand mode shapes. We can use this for a lot of different things, curve fitting one set of shapes to another. And we can get what's called modal participation. So we see the participation of each of the modes in the ODS, or let's say the participation of each FEA mode and each experimental mode shape if we had some of that data. These tools are very useful for comparing analytical data with experimental, and in this case we're actually expanding the experimental to basically get a nice clean animation. Mark, that's pretty much what I had to say. Well, let me try one of these hotkeys here. I'm going to go, we're animating at 2280 hertz, the ODS versus the expanded. Let's just go see what the two modes, the curve fit of two modes looks like. Okay, so there it is. You can see that the MAC value in SDI dropped considerably because I'm only curve fitting using the first two modes, the rigid body motion of the base plate and the bearing blocks. So that's not matching up with this experimental data very well because I just don't have a model with enough modes in it. Let me try the 6 modes. So now we're going to get all the rigid body modes in there. That is a 92%, 93% match. So 6 modes is sufficient at this speed to match the experimental data quite well. And if I go to 10 modes, there might be a little bit of flex in here, and it goes to 94%. So those higher frequency modes, there's a little bit of flex. They're getting excited at 2280 hertz in this machine. So this is a nice way to see how modes participate in operating data. So there it is down, and again we're at the high frequency, 2280 RPM, where the machine base starts to flex a little bit, and along with the bearing blocks, and I really need at least 6 of the modes from my modal model, and now I've got a 93% match. If I go and use 10 modes, I get a 94% match of the analytical modal model to the experimental data. Okay, Mark, I don't know whether we asked the audience for questions. They can send you emails. Have you received any emails?
I have not received any emails. There is a question area on the little panel. If you have a question, you can go ahead and type it in there. I'll go ahead and unmute everybody, and if anybody has a question, you can go ahead and speak. Let's see if this is going to work here. Okay, at this time, does anybody have any questions? Okay, I haven't received any questions in the question box either. You can always email us at mark.richardson@vibetech.com or mrichardson@vibetech.com, and we can get those out to you. Incidentally, we are recording this webinar, so we'll go ahead and get this posted to the YouTube site. We have our own Vibrant Technology YouTube site. You can search on YouTube and find it. And we have a recording of all of our past webinars as well. Okay, well, if there's no further questions, we'll go ahead and finish up. Do you have any final words? Ed? Okay, let's go ahead and wrap it up there. Appreciate everybody being on here, and we will talk to you next month.